So thank you again for joining us. This is the Inspire the Physicists of Tomorrow with Graphical Data Investigations virtual workshop that Vernier Software and Technology is bringing to you today. A little bit about Vernier. For nearly 4 decades, Vernier Software and Technology has been pioneering technologies and sharing our passion for STEM education to give teachers and students around the world more enriching and relevant classroom experiences. We are currently available in 150 countries and are in over 22,000 K-12 schools across the United States. So joining me today, you can see him sitting in his beautiful teal polo shirt. This is David Carter. He is our STEM training director here at Vernier Software and Technology. He is a former middle school science and math teacher, and he is somebody that you may have seen if you've attended any of our professional development workshops that we host throughout the year across the country. We provide different workshops to talk about the importance of data collection technology and go through a lot of our different sensors and probeware that we offer. But you may have seen David in person, or if you've ever attended any of our workshops at various conferences throughout the year, you may have seen him there. But he is here today to talk about some really exciting things, and I hope that you all enjoy your time. But first, we want to get started with a poll question. So I'll go ahead and open up the poll. We're curious, which of the following best describes your role? And we want to know, just so that we can get a better idea of who's in attendance today, so that we can make sure that we're speaking to you and why you've joined us. So it does appear that the majority of you are teachers, so thank you so much for joining us. I think that the material that David's going to review today is going to be really relevant to you. So from here, I'll go ahead and pass it over to you.
Thanks, Jess. So as Jess said, I'm David Carter, STEM Training Director for Vernier. I've been using Vernier probeware for almost 30 years now. I got my start when I ran the instructional physics labs at the University of Mississippi. So we were using early versions of these kinds of products on Apple II computers back in the day. So I've seen a lot of changes over the years. And let me do this here. So what we're going to be doing today, we're going to be talking about the importance of data collection technology. That's what Vernier is about, and how you might incorporate that technology into your classroom with your students. And lastly, kind of how that fits into things like NGSS standards or whatever standards that you have to use in your classroom. So we want to make sure this all fits into what you're doing here. So one question might be, what is probeware? So the idea with probeware is that you have a sensor that works in concert with a computer of some sort, and it allows students to make measurements, and then there are analysis tools and software that allows them to analyze the data. And so they get a real-time measurement of some phenomenon, and then they have the tools to be able to analyze that, and that's the important piece of there. And so what that gives you is they really get a deeper understanding of what's going on in the classroom when they do that. That's what the research shows. The visualization of the data is really key. The fact that they see something that what they just, they did something and then something else happened. And the fact that the two things happen simultaneously is very important. And then, the fact that they can be used to, teach students to predict and analyze and draw conclusions about what they've measured there. So it makes it easier to measure things that you can't do other ways. And so, so that's the kind of the gist of what's going on with probeware. For today's experiment, we're going to be using this GoDirect motion detector. And motion detector technology has been around for a number of years. It was really developed in the 1970s as a way of an autofocus for cameras. And physics teachers realized that they could use it to measure motion and velocity, acceleration, and whatnot. And the way it operates is that it sends out a pulse of sound out of here, and it goes out and bounces off an object and then comes back. And so it's using an echolocation to be able to measure the distance away from the object. It's kind of an electronic meter stick, if you will. And so the fact that it can do that and do it very rapidly means that you can measure movement if you want to. So we're going to be starting off, you'll notice it says the Go Direct Motion Detector, and we're going to do a ball toss. And we suggest something like a kickball or a soccer ball, something that has a kind of a hard surface to be able to use it with. Now, let me advance the slide here. So it's time to run our experiment here. So what I'm going to do next is I need to share with you some software here. So let me go here. I'm sharing with you my screen. And so what you're seeing there is my screen running Graphical Analysis 4. It's the software that interacts with this motion detector and allows me to do the data collection and analysis. And this sensor can be wired via USB, or it can be used Bluetooth. So it can be used wirelessly, and that's actually how I'm going to use it today. And the advantage of this, being both wired and wireless, means that you can use it across all kinds of different platforms. So our Graphical Analysis 4 software is available for 5 platforms, and it's free. So you can download it from Vernier.com for Macs or PCs. If you're using a Chromebook, you can go to the Chrome Web Store. If you want it for Android, Google Play, and iOS for Apple devices there. So it's the fact that it's available across all those different platforms is important because different schools are using different devices, and this gives you that flexibility with whatever you're using. The other thing about the software is that it looks the same across the different platforms. We did this deliberately because we want to make it such that you could be maybe in a BYOD environment. So maybe students are bringing their phones and you're using it. So it gives you a lot of flexibility with that. And so that it makes it really nice to be able to do that. So what you're seeing right now on my screen is just the Graphical Analysis 4 getting ready to do an experiment. And I need to turn the sensor on here. So there's a little button there, and it's now flashing a little red light. And that tells me that the sensor is available. It's on, and it's available for connection. Now, what I'm going to do is I'm going to go up to the part where it says Sensor Data Collection, and I click there. And you're going to find there's going to be a large list of Go Direct sensors that are available on this list. That's because I'm here in the home office and all of these different sensors are on. We're working on things, and that's why you're seeing all of those. And this could happen in your school. You could have a situation where you have all these devices going and you're trying to figure out which one is yours. Now, because this is Bluetooth, it has an individual ID number, and you'll notice that there's a place up there where it says Filter Device List. And the easy way to do this is that I'm actually just going to go in and I'm going to put MD, because that's part of the code that's there for the motion detector. And so it turns out that there's only one motion detector that's on and available. So it makes it pretty easy. So I can connect to that one. So I'm ignoring all the other possible Bluetooth sensors that happen to be in the building that are nearby. And so I'm connected to it now, and I don't know if you can hear it clicking. I'll hold it to my microphone there. And so it's clicking. That indicates that it's on. There's a little green light that's flashing that tells me it's connected to the computer in this case and ready to go. Now, if you'll take a look up here where it says Connected Devices, and then right down below that it says Sensor Channels. And a lot of these Go Direct sensors have multiple channels. And this is one of those, and it has different settings. And so by default, it's using what we call the motion setting. And that's for doing things like we're going to be doing where I'm going to toss a ball, or we may be walking back and forth in front of the sensor. That's really what that's for. The second part, where it says motion with a cart in parentheses, is for using with things like a small object, a car that you might roll down a ramp. It just does a better job of being able to track that object. Really what it's doing is it's turning down the signal strength on the sensor, and so it makes it a little bit better to track there. And then the last one, it says motion with TC, and that is temperature correction. Because the way that's working is that it's using echolocation, and so it assumes that you're doing it in air and that you're doing it at room temperature, which is approximately 20 degrees C. But that may not be the case, and the speed of sound changes at different temperatures, and so it would appear that the distance or the motion would change because of that. And so it's one of those things that's you have to be aware whenever you're using some kind of tool. How does the tool work? What is it doing there? So we're in the office. It's about 20 degrees C in here, so I'll just leave it there on the motion, and so I will say done. And so at this point, what you're seeing is my graph here, and I have a position on the left-hand side, so it's a position versus time as the default here. And that may be a little bit hard for you to see here, and I'm going to go up to the upper right corner of my screen window there and click on those three little dots. And what you'll find is that anytime that you're using graphical analysis, when you see the three dots, that's indicative that there's something else there. And it's a carryover from Chrome apps, and so it's in all of them it's that way. And so I'm going to go here and do it in presentation mode. And what it's going to do is make the fonts and stuff a little bit easier to read. So it makes the text bigger on the screen there. And so at this point, we've got the position time graph still, and let's take a look at it. The default for this is 0 to 2 meters, and our time is 5 seconds. And that's actually fine for what we're going to do. And what you'll happens with these different sensors is that there's kind of a quick and dirty setting that it'll go to that may make it easier for you just to get started. And for this one being the 5 seconds, it's plenty of time for what I need to do. If you decided you wanted to change it and do something a little different, you can go down to the lower left-hand corner where it says Mode Time-Based, and this is where you set your own collection parameters. But I'm just going to stick with what do I have now, and so I won't change that at all. I'll just hit cancel, but that's how you do that. And so at this point, what I want to do is I'm going to take this ball, and I need to throw the ball in the air over the motion detector. And I'm going to have to stand up to be able to do this because I need to be far enough away from the detector here. Because I can't get closer than about 15 centimeters, so I want to be far enough away. But I need to be able to toss it, and part of the toss that's key is that I have to toss it in such a way that my hands get out of the way, because it's using that echolocation, and I'm hoping that the sound goes off, bounces off the ball, and comes back, and not my hands or some other object. In fact, we actually have had little issues in our room here because there's a hard ceiling, and it's kind of weird, and so it bounced back some sound that we really didn't want. So you have to be aware of that with this sensor, just how it works so that you know how to best interact with it. So at this point, I think Jess is going to help me here. She's going to actually hit the collect button for me because I'm going to try to do this. And let me kind of demonstrate what the, see if I make sure you can see my hands there. When I throw the ball up in the air here, what I'm going to do is almost just kind of push it up and move my hands out of the way. So I go like that. I need to be watching the ball and not anything else. So I throw it straight up, and so when it goes straight up and comes back down. And if I do it right, then I will get some nice data there. So at this point, let's try it. Jess is going to hit collect. And I'm only worried about, there we go. I've got at least one good parabola there in the middle because I was kind of throwing it off to the side there. Sometimes it's a little bit hard to do when you're doing that. Sometimes I get lucky and do it right the first time. So let's take a look at this. So what I want to do is actually zoom in on the part of the data that's really of interest to us. And that middle section there is a good piece of the data. The other parts that you're seeing there, like the spikes and whatnot, is where the ball was out of the way and it was bouncing off the ceiling and not off the ball there. So I'm going to highlight that region, and then I go down here towards the lower left corner, and there's a little plus sign, and that's zoom to selection. So I've highlighted the region of interest, and so if I do that, then I'm looking at just the region of the data when the ball was going up and just is right there. So I'm ignoring the rest of the data there. And so at this point, we could go into some of the analysis, I'm going to do that in just a second, but let's take a look at some of the other views that we might have. Right now, it's defaulting to a position time graph, but you might be interested in, say, the velocity graph and the acceleration graph. And so I'm going to go up to the upper right corner here. And under View Options, I'm going to view 3 graphs. And so it's 3 graphs of the same data set there. And I need to do the same thing I did before, is essentially zoom in on that center section of the data. And so let me zoom in on all of that. And I don't quite have my times all lined up. In fact, what I might do here is come back here and make sure that I have everything at the same, so 2.5 to 2.7. Let me do the same one here. So all I'm doing is kind of selecting again to zoom in so that my scale factors are all the same there. Let's see here. Oops, I need to go back to this one. Let's see, 205 to 2.7. There we go. Okay, so now we're looking at the data, and it's 3 representations of the same data. And so, you know, if you're teaching physics, this looks very familiar to you. So you have position graph, velocity graph, and acceleration graph of that same data. And I think about trying to do this without a device like this. You know, I remember back when I was taking, you know, high school physics and we didn't have any equipment. We were trying to do acceleration graphs with stopwatches dropping balls out the second floor of the window. And it just, you know, the data was horrible. And it was really before this technology existed. And so that's how and why you might be using this. So, okay, so at this point, let's do some of the analysis. So I'm going to go up and click on that upper graph there, and I'm going to go to, there's the graph tools. There's a little icon there towards the upper left. It looks like a little graph there. When I click there, you'll see some of the tools that are available for data analysis. And so these will be the tools that when you do some lab, it's going to refer to these and have the students look at them. And so for the first one, what I want to do is I'm going to apply a curve fit to my position time graph. And so we go here. And the way graphical analysis it works, if you do a curve fit, by default it just says, hey, I'm going to try a linear fit, and it kind of lays it on there. Now, until I hit apply, it's not actually applying that fit. And what I can do is I can come here and try out, you know, different fits here. So I'm just going to go cut to the chase and go straight to a quadratic fit. We might recognize that it is a parabola, and so I go there and apply that. And then if you look up here towards the upper right corner there, it's giving me the equation y equals ax to the b, and my a term there should be 1/2 the acceleration due to gravity, and I'm getting negative 4.9, which is, if it were 2 times that, it would be negative 9.8. So we're getting beautiful data with that. So the ability to be able to analyze that so quickly is pretty nice to be able to do that. And so that's analyzing the position time graph. Let's do the same thing. I'm going to come back down here and click on the velocity graph. If I can click there. Well, there we go. Got to get my trackpad working there. So I'm highlighting that center section of the data when the ball is undergoing uniform acceleration. And I'm going to go here and say, hey, let's apply a curve fit. In this case, linear does apply. And so I can go here. The slope of that line is going to give me the acceleration due to gravity. And I didn't select exactly the same part of the data there, but I'm getting a very similar value to what I had for the full quadratic there. And then lastly, what I might want to do is come down to the acceleration graph. And so down there, we see that there's a constant section. We know that the ball is being tossed in the air. It's undergoing uniform acceleration due to gravity. And so I might want to get just the average value of the acceleration there. So I'm going to come here and highlight maybe the region there. And then also under that graph tools, go there and do view statistics. And maybe the average value that's there gives me the acceleration due to gravity, negative 9.8 meters per second squared. So that should make any physics teacher happy to be able to see that. So this is one of the labs that's in our Physics with Vernier book, and so it has them be able to do that. And it's kind of nice because you can do it in kind of in a confined space to be able to do that. Now, what I want to do next is I'm going to kind of switch gears a little bit and show you another way that this sensor is commonly used. There are lots of activities that have the students walk back and forth in front of the motion detector, and it's displaying that real-time graph of what they're doing. And one of the things that happens with that is there's an option for students to be able to do a motion match or a velocity match so that it puts up a graph for them to be able to try to match it with their body walking back and forth. And what that requires them to do is to do real-time analysis of the data that they have. They have to be able to pull it apart to be able to do this. And I want to kind of show you what that looks like. So to do that, I'm actually going to do a new run here. I'm going to do actually a new file here. So I'm going to do new experiment. And it's asking me if I want to save the work. It was awesome, but I won't save it. I'll do it again some other time. And so now we're back to here, and I'm going to go back to sensor data collection. And one thing you're going to notice is it's going to go right back and reconnect to the sensor. Because I connected to it the first time, it goes back and connects to it, which is actually really handy in this situation. And so when I go back, it'll be right back to kind of where we started with that position and time graph back to that original setting. And then we're going to do this. I'm going to go down, and under that graph tools, you'll notice down in that lower left corner there, it says add graph match. This only exists if you're using this sensor in the software. If you're not using a motion detector, it doesn't say add graph match because it's not available because it's only as a part of this one there. So I'm going to go here, and I want to do a position match. And so it's drawing this graph and asking the students to be able to replicate it. And think about what's required. They've got to be able to pull this apart. And one of the things that I've done quite often with students is that if I'm using the motion detector with them, I will get them prepared for this part of the experiment by having them do 6 graphs. I have them walk very slowly away from the detector. I have them walk slightly more quickly so they can see if they're going away, what effect does that have on the slope? Is it positive, negative? The actual slope itself, how steep is it? And what does that tell you? And then I'll have them do a graph where they walk very slowly towards the detector, and then one where they walk a little bit more quickly towards there. And again, it's getting that relationship of what's this sensor doing. And then I have them stand still a couple of different distances, so maybe 1 meter, maybe 2 meters. And what does that graph look like? And that prepares them to be able to do the actual matching function here. And so if we look at this, if we've done a little bit here, we can see that this part where the slope is negative, and the students figure out, oh, that means you're going towards the detector. And so they look at that, and then maybe they look at this section in the middle. What does that mean? You're walking away from the detector, and then what's happening here? You're turning around. Now, you may notice that our timestamp is different. The match ones always go to 10 seconds, so it gives you a little bit more time. So it's longer than the default for the ball toss there. And so I'm going to try to match this, and I think Jess is going to help me here. And so what I need to do is I'm going to actually turn this so it's aimed at me. And we've got it here on the table. And one of the things that we suggest with this is that you carry something, if you're going to be walking back and forth of it, you carry something that provides a good echo. So I'm actually going to be using our Physics with Vernier book. I've used pizza boxes and cardboard, whatever, so that it bounces that sound off. And we found that if students are doing this in the wintertime and they're wearing really fluffy clothes, the sound doesn't bounce off them. And it's a whole other lesson in physics. But in this case, we want it to reflect. And so I'm going to actually carry this with me here. So at this point, I'm going to stand up and get this out of the way there. And I think Jess is going to maybe adjust the camera a little bit there. So I'm going to be holding this in front of me. And what I need to do is think about, what does the graph tell me to do? It's starting off, it's saying, well, I'm supposed to be 1.25 meters away, and I am too close. And you may notice that there's down in the lower right corner, there's actually a little meter there. And so I'm getting back here. I have about I can't quite see the computer screen at this point, but I think I'm about far enough away. And so Jess is going to hit the collect button there, and so I will slowly walk towards there, and then maybe I walk away, and then I'm supposed to go here, and then aha. So let's talk about this. So, I sort of matched it, and when I work with students with this, I try to emphasize that I don't really care whether or not they can actually match it. What I care about is, do they understand what's happening here? And so if we take a look at it, the section, the first third of the graph there, am I going in the right direction? Yes. How do we know? The slope is both negative. What about my speed? Was I going fast enough, too fast, whatnot? The slopes seem to be about the same. So the students often they'll get to the point they'll say, oh, you're going the right speed because the slopes are the same. And then the center section, kind of the same thing. I was going the right direction. My speed, maybe I was a little bit slower than I should be. And then the last section, I went the right direction, but deliberately I was going too fast. And, and the students could look at that and say, oh, yeah. And I would ask, why are you going too fast? And I'd say, well, your slope is too steep. And if you think about what's happening there is that interaction, they're thinking about what does that physically mean? And it's really interesting to work with students when they're doing this. And in fact, years ago, I was working with a group of students, and I did exactly what I described about the 6 graphs, and we went through all of this, and we got down to the part where I was having them do the matching, and I forced them as a group to let's talk about what it means. And they were telling me exactly what it meant. They knew that that first section of the graph was walking away towards and whatnot. Now, this was a group of 6-year-olds. It was a science day camp, and they were interacting with this data. And at the time, I was teaching engineering physics at the university, and the students who were coming in the labs couldn't do that. They couldn't have pulled that apart at that point, but these young students could, and it was because of that interaction with it. And that's what the research shows about it, is that this interaction with it is what is key. And so it's definitely a great tool for being able to enhance the student learning there. So, okay, so at this point, let's see, we want to go back here and let's see if I stop sharing that. So no matter what you teach, it's going to be important that you are meeting your standards. And you'll find that devices like the motion detector here fits into standards. And so we'll take a look at a couple of these things here. I'm not going to read them to you, but if you're doing NGSS, you might be interested in the science and engineering practices. And so these are some of how this would fit into those parts of the standards. So obviously analyzing and interpreting data, that's what's happening real time there as they're interacting with it. And then using mathematics and computational thinking. So they're putting the math to this, and that's very important. And then disciplinary core ideas, where you're getting into the concept of forces and motion, uniform acceleration, things like that, and gravitation. So all of those things play into the use with this device. And then cross-cutting concepts, the patterns. The fact that when you toss the ball, there's this certain pattern. So they start to notice, oh, if I do this, I end up with this pattern. And then systems and models of systems. We're actually kind of, we have our boundary conditions there when we're throwing the ball up. So all of this fits into the standards there. And so kind of in summary, the reason we do this is that it helps students better understand the topic at hand. And so it kind of deepens their understanding with this. And it's very engaging. I know from my experience over the years that students love using this device, and you can really get them engaged in it. I've had situations where it was hard to get them to break away. Hey, it's time to stop, and they're like, oh, we're doing this. I want to try something else, and that engagement is so important. And then part of that is inspiring to them, meet standards. They are doing something they enjoy, and with that, they are learning something. You're kind of tricking them into learning something, I guess. But so hopefully you found that useful for today. And so at this point, let's see, we want to do this. And there I am. And then lastly, we have a little Q&A session. So if you have some questions you would like to ask about the motion detector in this case, or other questions involving Vernier products, feel free to ask those. And I think Jess is monitoring the chat line here, so she may read them to me.
Thank you so much, David. Yes, if anybody has any questions, please feel free to drop them into the chat now. One of the things that I know that we often get asked about, and you covered it earlier, but for those who maybe weren't able to join right when we started, if you could just let us know, how do people get graphical analysis? How can they access it?
Well, it's very easy to get graphical analysis. It's available for 5 platforms, and so if you want it for Mac or PC, you go to Vernier.com and you go to the download section, and when you click there, you'll see a link to it. And so if you are using those devices, you'll actually download it from us. And if you want it for Android devices, it sends you to Google Play. For Chromebooks, the Chrome Web Store. And then for Apple devices, it's under the App Store for those devices. And so it's free. Graphical analysis for, and the fact that it runs on all these different platforms, some places are using it with their cell phones or iPads or whatever, and so it's definitely worth having there.
All right, so we just got a question. Does graphical analysis have the same options available on all 5 platforms, or is it more robust in the Windows environment?
It's really designed to be the same across the different platforms. What we want to do is to make it such that it's platform independent. And so when we change it on one, it changes on the other. So they really are identical across there. There's a few little differences and a few parts that we didn't go into, like if you have a device like a phone or an iPad that you might take a screenshot that you couldn't do on a computer, and it has a little different way of doing that, but really it's the same, and that's our intention, is to have it be the same across all those platforms so that it doesn't matter. We don't want people who are not using Windows machines, to feel left out, and so the intention is for it to be the same across all those platforms.
All right, and one other question, David. Other than the graph matching experiment that you did and the ball toss, are there other available experiments that work with the motion detector?
Yeah, there's a whole host of different ones. And, I already mentioned maybe using it with a cart and track, so you're rolling maybe a car down in front of it. Some other physics things, you might be doing impulse and momentum experiments where you're doing a collision, and what you're trying to do is measure the velocity. So it's allowing you to be able to do that. There's one that's not really related to physics so much, but there's one in our earth science book where you actually model or mimic what's happening with sonar on a ship. And so you can set up kind of a simulated seafloor, and it has you move across the seafloor. And so maybe you're measuring the height of the different mountains there. So this used across the curriculum. I know it's in our elementary book, middle school physics, and so it's a very widely used sensor.
All right. Well, that is all the questions that we had. So thank you so much, David, for your time. And we did get one more question. Hold on.
We have time.
This individual says that they teach for a cyber school, and their students are spread throughout the state. They have GoMotion and share their Logger Pro screen as they collect data. If students download graphical analysis, can I send them my collected data for them to analyze?
There you go. So what happens is that once you've done the experiment, you can save the file. So you could have some data that where you have saved that file, you send them the file via an email, or they pull it out of a folder someplace. And as long as they have the app on whatever device, they can open it and be able to do the analysis. So that would be a great way to be able to do, kind of the distance learning model there. So sure, that you could create your own data for them to analyze.
Great, thank you for these questions. We have someone else that Jill just asked. She has some older sensors, and so if she were to update the software, will it work on the older sensors?
Yes, it will. You need to make sure that you have the right hardware to make it work. I mean, I was using the NuGo Direct, using it wirelessly here, but graphical analysis does support the ability to use our LabQuest line of sensors through the device, and there's multiple ways. I mean, we have our kind of the cheapest is the Go Link. You can plug that in. Our LabQuest Mini allows you to plug in our older sensors to the computer in this case to be able to do it, and that would require me to plug it in. We have a LabQuest Stream, and the Stream actually allows you to use those older sensors wirelessly, so you could use them, say, with an iPad that way. And so they're definitely supported in the software and in hardware devices there, and that's kind of one of the keys to Vernier. Our founder was a high school physics teacher, so we know what it's like to be in the classroom, and we don't want to pull the rug out from under you. So we try to make sure that the older devices will work with it. So yes, there's definitely a way to do that.
All right, I think that is all of the questions. And so Jill is asking where she would need to go and get it. So Jill, I will go ahead and drop in our website URL that you can go to, but also you can email our support team at support@vernier.com. I'll also drop that in there for you. And that way you can contact them directly, and you're also welcome to call us. We have people on the phones that are ready to help you, but that way you can let them know what sensors you have, and they'll be able to figure out exactly what will be the best fit for you, and they'll walk through that with you so that they can find the best solution. But right now, I think we have reached the end of our time. I just want to thank all of you for attending. This has really been such a wonderful experience. This was our first virtual workshop that we were doing in this format. So thank you so much for joining us, and we look forward to connecting with you again in the future.